and the sharing. Okay. You did receive today, this morning, a file from me that I'm going to use today, haven't you, guys? It's about transportation.
Yeah, I got it.
You got it. So that's for those who want to use it as we are doing it. And I'm demonstrating things. Some students like to do it on the spot. Okay, so the first topic that I want to work on is the good old blending problem that is represented by this diagram. This diagram shows 3 ingredients that are mixed and create 2 products. This is a super gasoline and this is a regular gasoline. And this needs to have at least 90 octane and this needs to have at least 100 octane. And you achieve it by mixing different ingredients that have different octane quantities in them. And there is a supply restriction. You see, this is the supply restriction here. And there is a demand, maximum demand that you should not exceed. There is a selling price for each one. And there is a purchasing cost. Everything goes per barrel. Well, you take differences, then you take and calculate profits. Naturally, the objective here is to maximize profit. So this is the objective function that we maximize, where the variables are the blending variables. How many barrels of ingredient 1 you mix with other ingredients in order to create regular gas, and how many to create super. So for each one of these combinations, you have a profit because you take the selling price minus the purchasing cost per unit, per barrel, but here it's the same selling price, but a different purchasing. So the profit is different. And this is to be maximized. And then we have supply constraints and we have demand constraints. On the supply side, you cannot exceed the available amount of 110,000 barrels of ingredient 1. So when you add what you use of it to sell as regular and add to this what you sell as super, those together cannot exceed 110, and the other 2 are the same. And here you add the ingredient 1 regular upon ingredient 2 regular and 3, that's the mix. For regular gas, cannot be more than 350 barrels because that's the maximum demand. There are other constraints on the octane, which I discussed with you last time, how to make them look linear. Our sensitivity analysis will focus on these 2 groups because this is unique. Okay, so this is the model. As we enter the model like we did last time in Excel and run it in Solver, we got the sensitivity request per request. And these are the 2 parts of this report. This one is the one I'm not going to talk much about. And I'll have an opportunity to talk about it when you go to transportation. The reason I don't want to get involved with this here is if you look at the structure of the range of optimality. Remember, the range of optimality, say allowable increase, is how much the objective coefficient can increase before the optimal blend is going to change. That's here. What it tells you that it will never change. Why? The allowable increase of the number 2 is infinity. You can increase the profit on ingredient 1 when mixed to be sold as a regular gas. You can increase the profit indefinitely because the allowable increase is infinity. And the optimal solution will not change. Specifically, you will still buy exactly, meet this is the blend amount that you have available for ingredient 1, you will still purchase this amount of ingredient 1 and sell it as regular. And the question is, how come? If this $2 per barrel increases to 20, it's 10 times more. Still, you are going to only sell 110, only mix 110 barrels of ingredient 1 to sell as regular? Why not more? The answer, you don't have more. This is the supply. So you are already at the maximum allowed, which explains why this can go to infinity, nothing will happen to the solution. But if this is the case, there is not much I can do with you on that. Even more is the other number here. The allowable decrease is practically 0. It tells you that you can reduce the number 2 by 0 before the optimal solution is changing. So every little change in reduction in the profit of $2, say $2.99, 1 cent less, this optimal blend is going to be somewhere else. This means that the solution is very sensitive to reduction in the profit. So if the profit was for some reason overestimated, when you say 2 here, this is very bad because every little drop in this will change the optimal solution. That's all what we can say, and every single range of optimality here has the same structure. If you have infinity and 0, then you have infinity and 0, then you have 0 and 0, this is even worse. Then you have another 0 and 0, 0 and infinity. So it's a very unusual situation that is typical to blending problem under certain cost structure. So I don't want to discuss this sensitivity based on an unusual problem. I'll do it with the transportation, there we will not have this problem, okay? But when it comes to the constraints, here we don't have any unusual phenomenon, and therefore I'm going to focus on that. The demand for regular gas decreases by 10,000 barrels. First thing you need to do, identify in the model where is the change going on, where is it? So we are talking demand for regular gas, demand for regular gas is here. So this is the constraint that is changing. What value is changing? The right-hand side. This is the one that is changing. So the demand, this is the maximum possible demand of 300K barrels for regular gas, given. Now they say, management think that the demand will drop by 10,000 barrels. What happens to the total profit? Management is worried. The demand is less. What will happen to the profit? Well, we can answer right away from sensitivity. But I would like you to take a look at common sense before. Indeed, the maximum demand, that's the maximum possible demand, 350,000. What do we do in our blend? We only satisfy 260,000. So we leave unsatisfied 90,000 barrels. And this is optimal. It's part of the optimal solution. So now that the maximum demand is dropping to 340,000, what will happen? In fact, nothing. Nothing will happen to the optimal solution because you even now do not try to meet 340,000. You don't try to meet any demand above 340 because you stop it to 60. So no wonder I'm arguing nothing will happen to the optimal solution, and therefore nothing will happen to the total cost, to the total profit, nothing. Now, let's see how is this being reflected by the results of the sensitivity analysis. So, answer. The allowable decrease is 90,000. Do you see here? That's the allowable decrease of this constraint. So this can drop by 90,000 before the shadow price will change. So because 10,000 is falling inside the allowable range, the shadow prices will remain zero. But the shadow price is the change in the objective function per 1 barrel increase. And because you have a 90,000 allowable decrease, the shadow price will remain zero, even if it goes down to 340. So there will be no change in the total profit because you calculate the change in the profit as the shadow price times by how much the constraint have changed. Only the good news, the shadow price is zero. So there will be no change in the profit. And the profit is achieved by this blend. If the profit remains the same, the blend remains the same. And therefore, this blend remains optimal. So when is it that a constraint is changing and the optimal solution remains optimal? If the constraint is non-binding. This right-hand side didn't stop the solution from improving the profit because you stopped short of it. So you have a slack, we call it a slack. Once you have a slack, the shadow price immediately will be zero. If so, once the constraint is either increasing by unit or decreasing by unit, as long as it's falling inside the range, the optimal solution will not change and the objective function also will not change. This is happening when the constraint is non-binding. Now we have two cases, remember, in which a solution does not change. Last time, it was when the objective coefficient is changing within the allowable increase and decrease, then the optimal solution doesn't change. And now you see that when the constraint is non-binding, but the right-hand side is changing within the allowable increase and decrease, also the optimal solution will not change. And so is the profit. The objective function also will not change. You will always see that when you have a non-binding constraint, the shadow price is going to be zero, always. So this was the first question. And now comes the second. The supply of ingredient 2 is expected to increase by 15,000 barrels. So how will the profit be affected? What constraint is changing now? So we are talking supply. So it's one of the supply constraints. Ingredient 2. So we have this constraint here. Okay. What is the value that is changing? The right-hand side. By how much? Plus 15K. Therefore, naturally, you are going to look at the allowable increase, which is equal to 90,000. What will the profit be? How will the profit be affected? Well, take a look. This one is increasing by 15K. 15K falls inside the allowable increase. The 450 as the shadow price remains 450. The increase in the profit therefore will be 450 times 15,000. And that's how you will find what will be the new profit. Okay. And if you look at it by making sense out of it, what you did before, you already used all the available ingredient number 2. You see it's binding. This one equals, so this means binding. So this availability did stop you from improving more. If you add more to the available amount, you will make more profit. But this is only if you are going to use the additional 15,000 barrels. If we argue that each additional barrel is adding $4.50, we are behind the scene also saying we are going to use this 15,000 additional barrels. But then if we do, we have to change the optimal blend, because the optimal blend from before did not use 15K. Now it is going to, so the optimal solution is going to change. And as you see that the optimal solution is changing when a constraint that is binding is changing inside the range of feasibility or within the allowable increase and decrease. How much it is changing is controlled by the shadow price. That's about this question. I have one more interesting question here. Currently, per barrel, management is paying $14 for ingredient 2. What is the maximum that management will be willing to pay for the additional barrels of 15,000 barrels of ingredient 2? Well, each additional barrel is increasing the profit by $4.50. So for the additional amount, management should be willing to pay $14 that they already paid, plus maximum of $4.5. If they add more than $4.5, they lose money. So the shadow price will tell you what is the maximum management is willing to pay for one additional barrel. As you see, shadow prices are very, very strong measurement for decision making. And therefore, it is important to understand that, and that's why I'm talking about it again. Okay. We'll come back to this in transportation, which is the time to move to transportation problem. Transportation problems are those coming from the logistics. Logistics is a huge area in optimization, in operations in general. Transportation problem specifically is dealing with shipping a commodity from a set of locations to another set of locations. But as you see, the problem is described here as a network. There are a variety of network problems, all of them logistic type. One would think of, there is one, it's called the shortest route problem, which means you have a big networks of roads and intersections, and you want to move from city A to city X at the shortest possible path. And there are so many ways of doing it because the network is very large. What is the shortest path? It's a logistic problem. But we are doing transportation. Transportation can be huge problems. We are doing a very, very, very small one. Maybe later you'll see one that's slightly larger. Because those transportation problems can become very, very large, there are specially structured algorithms, not simplex, that are much better for those kind of problems. They can be linear, that can be non-linear, and we are focusing on linear programming only. So this problem is number 16, taken from the book, and it represents a very simple transportation problem. A commodity needed to be sent from Jefferson City and Omaha to 3 cities. In Jefferson, assume you have a plant, and in Omaha, another plant. They produce exactly the same item. The capacity of production in Jefferson is larger. Maybe the plant is working 3 shifts a day and it's only 2 shifts. Anyway, the capacity here is 30, capacity here is 20, which is the maximum that can be shipped from each city out. There is a demand for the item in each one of the cities. In Des Moines, 25, Kansas City 15, St. Louis 10. Each unit shipped from Jefferson City to Des Moines costs you $14 as it is being shipped, called transportation cost per unit. But from Jefferson to Kansas City is 16. Why would the shipping cost be different? That's maybe they are using different means of transportation. So on each arc, that's what we call it in network. These are called nodes and these are called the arcs. On each arc here, you have a different unit cost. What's the problem? You have to ship the items from Jefferson City and Omaha such that you don't ship more than the capacity available in these two cities to Des Moines, Kansas City, and St. Louis such that the demand is satisfied at minimum total transportation cost. That's the problem. Notice that this problem is balanced in the sense that the total supply here is 50 and the total demand here is also 50. And just ignore the 20 here. I need to delete it. 20, 35, and 25, and 50. So 50 by 50. This has an implication about how the problem is to be formulated. It's called a balanced problem. Now, the variables called x sub ij. I stands for the sources. So this set of constraints are the sources or supply points. And these are called destinations or demand points. I stands for the supply. J stands for the demand. So X sub ij will be how many units are shipped from source I to destination J. This is a very common notation used in networking because it's very convenient to do. Now, the objective function is to minimize total transportation cost. So you'll have $14 here per unit shipped from I1 to J1. It's called X11. Notice I don't say X11, X11. 14 times X11 will be the total shipping cost along the route from 1 to 1. Then 16 is the second one. So this will be 16x12 is the total shipping cost from source 1 to destination 2, and so on over all the total costs, or the shipping costs along these paths. And now, what are the constraints? Now, notice that because the problem is balanced, you cannot give up on any units in the supply side, because if you don't ship, example, if you don't ship 30 units from here, one of those here will have a shortage because it's 50 by 50. If you don't ship 50 out, you will not receive 50 in. So what it says here, that all the supply must be used and all the demand will be satisfied. Therefore, all the constraints that are upcoming will be equality constraints. Here's how. The supply constraints are those that are shipped from Jefferson City and Omaha. Jefferson City is 1, and Des Moines is 1. X11 plus X12 plus X13 is the total supply shipping from S1, supply point number 1. And this needs to be equal to 30. And the same for Omaha, equal to, because I know that I have to ship all the units available. Then come the demand constraints, okay? So now I'm looking at the units shipped to the demand point, one being Des Moines. What is shipped to Des Moines? From source 1 or from source 2. Combined, it has to be exactly equal to the demand of 25. And then Kansas City and St. Louis will be the same. Okay? That's how you build supply constraint and demand constraints. And this is the classical transportation model. The problem, though, is balanced. One would wonder, why would the total supply be equal to total demand? Demand is created by environments, markets. The markets are not constant. They shift from month to month, say. Today, demand for cars is not very high, but it used to be high just 3 months ago. The environments are changing. So to solve this problem as a balanced problem is nice, but how useful it is? Well, I'll tell you something. Mathematically speaking, extremely useful. In fact, all the algorithms that I mentioned are specially structured to solve those are solving balanced problems. But what if the problem is not balanced? That there are techniques developed in order to make them balance, and now the algorithm can be used. So therefore, it's important to understand the balanced problem. Besides, as I move to an unbalanced problem, I'm building on that one. So it'll be very easy to understand. That's why I did that. Here is an example of an unbalanced problem. Look what I did. I changed the supply in Omaha from 20 to 30. This may occur if a new technology has been introduced. This may occur if another shift is introduced. This may occur if more recruitment of workforce. So supply capacity can increase. Now, this is more practical question than the balance problem, just for a practical approach. Usually, the supply will exceed the demand. Why? Machines or production lines can produce faster than what the market is producing as demand. So this is a very practical question. How to solve this problem? Well, first of all, you have to set up the model. Since the supply exceeds total demand, as you see, 60 versus 50, you don't need all the supply available to meet all the demand, but the demand needs to be met. So therefore, the shipments from a source don't have to be equal to the capacity, maybe less than the capacity. So the constraint will change to less than or equal to. And on the demand side, you will keep it as equal because you want to meet the demand. Here are the supply constraints. See? Now you have 30 and 30, and both are less than or equal to. Now, why both? Because you don't want to determine for the model which one is going to be the source that will not work full time. You want the model to decide based on cost minimization. And what will happen here? These are the demand constraints. They will remain equal to. When you solve this model, all the demands will be satisfied because of these constraints, but not all the capacity will be satisfied. One or both will work under capacity. That's unbalanced when the problem is having a supply that exceeds the demand. Sometimes the opposite is happening. Now I went back to 20 here, I add 10 units here. So now demand exceeds supply. If demand exceeds supply, you are rest assured, not all the demand can be satisfied. So since the demand exceeds the supply, not all the demand is met, yet all the supply must be used. So we switch the equal to and the in equal to. What happens here is the shipments will be satisfied, the capacity constraint will be satisfied fully, but the demand constraints will not. So there will be at least one demand point here that will have a shortage. We will have to deal with these shortages sometime else, I guess next time. Because shortages, sometimes you penalize yourself for those. So we'll have to see what we do. Right now, we'll just report to management that we cannot meet all the demand under these conditions because our capacity, total capacity, is not large enough to meet. And looking at the shipping costs only, that's the plan that will minimize those costs and will solve the model and provide the solution to management. Here is how the model looks. The supply constraints are now equal to, but the demand constraints are now less than or equal to. So this way, you have three models for each case. The balance problem will be fully equal to. Supply exceed demand, you'll have less than or equal to on the supply constraints. Demand exceed supply, you'll have less than or equal to on the demand constraints. And then you'll see another discussion that I have about those signs, equal, greater than, equal. In the book, they take some shortcuts. I like it more. This is more intuitive for students, for myself also. Then comes the sensitivity analysis of this problem, but I'll stop here and I'll go to Excel. And this is the file that I sent to you, and we'll run it. We'll get the optimal solution. Before you go to sensitivity analysis with me, I want to show to you something on the linear programming itself. Then with the time that is left, we'll come back to this PowerPoint. Okay, so. Yeah.
Come and see.
What?
Come,
Oh, you didn't talk to me, huh?
Talk to me. Come. Look at him.
Stop with this.
No. There's no camera.
I'm showing to you now the transportation linear programming model of this balanced problem. Okay. So for this balanced problem, in fact, we have to have equal. And I took here to show to you that it doesn't have to be equal. You can allow yourself to not write equal, although in the optimal solution, you'll get equalities, guaranteed. So why is it so? And that's what the book is doing. We minimize cost. We write for the supply here less than or equal to, and that's because we are not going to supply what we don't have. So these less than or equal to guarantee that you can only supply what you have. You write here on the demand greater than or equal to because you don't want to create shortages. So either you ship more to a demand point or exactly what the demand point needs. What will happen for us when this problem is solved? There is a minimization mechanism that minimizes the total cost. So this mechanism is trying to ship as little shipments as possible to minimize costs. Therefore, it will not ship to the demand point more than the demand. It will only ship the demand, which is the minimum allowed. So because of that mechanism, the demand constraints will be met as equalities. You don't allow to be less than the demand, you allow to be more or equal to the demand. It will take the equal to because this is the minimum amount allowed. So all the constraints because of this mechanism will be met as equalities. But if these three are met as equalities, now by definition, you have to have enough capacity to meet those equalities. So these will always also be equalities. So yes, you can write the equalities like I wrote it before because it was intuitive, but you can also write it this way and you get exactly the same solution. That's what I want you to see. So now let's look at the model itself. Here are the variables. So you have six, yeah, because you have 2 by 3. And here we make a room for all the values of those variables. Here you entered the objective coefficients, which are the unit shipping costs. And now come the constraints. You should be familiar with this notation. We have seen it in previous problems. So from source number 1, S1, source number 1, you ship to demand number 1, demand number 2, demand number 3. Yes? So therefore, it's x11 plus x12 plus x13, therefore the 1 here and here and here. And then 1 here and here and here. These are the supply constraints. The demand constraints will place 1 here and 1 here because now we are combining the quantity shipped to Des Moines. 1 here and 1 here is Des Moines, coming from 2 different supply points. So that's why 1 here, and then 1 here, and so on. The model has a diagonal kind of structure, this matrix. And the most important thing about this matrix is that these columns have 2 1s and 0s, 2 1s and 0s. If you have a large matrix like this, because you have many sources and many demand points, always you'll have 2 1s and many zeros. This is why simplex is not efficient algorithm. I can't go into the mathematics here, but that's the reason that new algorithms were created, because so much work was wasted, done by simplex, and that's why it was slow in solving such large problems. So that's just a comment. Here is the sum product for you to see it's not different than any other problem here, you see? And if I click on the next one here, this one and this one, not different than any sum product that you might have done before. Here's the last one. See? So it's the sum product, and we'll enter now the constraints into solver, okay? I may already have a model there. It might not be this one. Let's see if I have, no, I cleaned it up, great. You, in the file that I sent to you, might have a model. I don't know that it's exactly the model that I'm going to do now, so you'll have to compare. If not, then you'll have to delete it and do a new one. So let me tell you what is the objective function that I'm going to place. This is H3 is my objective function. Do you have H3 as your objective function if you open the file? Anybody can open the file?
We don't have that one.
G21.
You don't have H3 as the objective?
No.
No, also delete. Delete the model that you have, because I'm going to redo it, and then you'll have it, unless you don't care and you let me do it and you don't want to repeat it, and then you can keep the model that you have. It's a different formulation of the same problem that I want to do. But if you do want to follow what I do, then you have to delete what you have now. Should I wait? Tell me. Are you deleting?
Yeah.
Yes. Okay. So, and you know how to delete the variables here. That's easy, right? Just highlight and click the and press delete.
Okay, thank you.
But the constraints is not. Constraints are different. Highlight a constraint and then click delete in solver. Do you know what I'm saying?
Yeah.
Okay, and then the second constraint, do the same.
Okay.
Good.
Thank you.
So guys, I enter the objective function here, and now I am entering the variables. And the variables will be from here all the way to here. So B2 to G2 are the variables. And then you add constraints. So here are the first two constraints. I select them together because both are less than or equal to. Okay, less than or equal to, and then I select 30 and 20 together. Okay. And now I'm adding the demand constraints. So I click add. I enter the last three constraints sum product, which has to be greater than or equal to. So I am changing it. And then 1, 2, 3 on the right-hand side. If I click OK, you will see the two set of constraints. Okay. Mahmoud, are you with me?
Yes, sir.
Yeah, so you're done. Okay, good. I can solve the problem because I check that it's non-negative. I have it from last time. And I see that the simplex is already selected. I'm solving. And I did click on sensitivity to get it and then copy it into PowerPoint, but I will not do it now. Here, you ship 5 units from Jefferson City to Des Moines, and 15 units from Jefferson City to, I don't remember the city. Okay, so let me say, from S2 to D2, from S1, it's X1 to 15. So from S1 to D2, 15 units. But you see, from source number 2 to the demand point number 2, none. And from source number 2 to demand 3, none. From source number 2, 20 units to demand 1. That's the only demand point that is getting units from source number 2. That's what it tells you.
There was a question.
Yes.
Alex had a question.
Go ahead.
Yeah. How do you know if you select max or minimum in Solver?
Minimum. Yeah, we are minimizing costs.
Is it always minimum?
On transportation?
Or like in general? Like the problems we do in this class?
No, you forget. We started with the profit of the plastic, of the Space Race and Zapper, which was maximized.
Oh, okay.
Right? And we had other problems in which we had maximization. In blending, we had a problem on maximization of profit. Do you remember? Just a few minutes ago.
Oh yeah, I got it. Yeah, thank you.
Each problem is different. Okay, so and notice the constraints are all binding. You see, equal, 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 equal. That's what I predicted will happen, and this is what is happening, although I didn't force it. I did not write equal to on the constraints. I did not. Now I want to show to you something that is very useful when the problem is starting to grow. Problem grows in transportation very fast. Suppose you don't have only 2 plants. There is a manufacturer, it's larger, it has 5 plants all over the place in different cities in America. And it's shipping to 12 markets all over the place in America, including Mexico and Canada and anywhere, geographically very far away. And that's not an unusual situation, very usual. Now you have 5 sources and you have 12 destinations. 5 by 12 make it 60 variables. Yeah, x11, x12, x112, x21, x22, x212. 60 variables. If you take this method and place here 60 variables, I'll need, even on my large screen, like 5, I would say 5 screens. And nobody works this way, nobody. So you have to find another way of organizing the linear programming. I want you to see that. It's very compact. It helps in networks. It helps in transportation. It will work in the assignment problem that you will see. it's very, very neat and very revealing because the solution becomes very intuitive. You'll have to know how to set it up as a spreadsheet model. So it's the same model, only reorganized. I'll do it here. That's the model that you see in the one that I sent to you. I organize it here below, but I'll do it here now. So if you need adjustments, make the adjustments. Take a look. I'm organizing the input in a table. It's rectangular. Whenever you do it rectangularly, do it. So you have 1, 2, 3 for the demands and 1, 2 for the supply. It's a little tiny problem. Just imagine it was 10 times larger and you'll appreciate this method. And so that it is a little bit more neat, I'll put a frame around. Okay. Here will be demand 1, demand 2, demand 3. Source 1, source 2. You can even write the names of the cities, Jefferson City and Omaha. You can even write those. Some people like to do it, you know, because it's more understandable. And then in here, I'm entering the shipping cost. This is the input. Remember the input. So it goes 14, then 16, then 7. This is the shipping cost. And here I'll put 8, 10, and 5. 8, 10, and 5. Okay? Unit shipping costs. Just for your information, I am adding myself here the total supply of S1, which is 30. So I write it here. And then I write here 20. That's the supply. And I write the word supply here. And demand. So I'll have 25, 15, 10. This is, oh, okay. That's it. Now, I copy this table so that I have the same dimensions. And I put it here. I clear it up. Here will come the variables. The variables, then I'll put something to remind me that here I have the variables. So this is it. Now I know these are where the variables. It will be x11, x12, x13. You follow? 1, 2, why not 3? D3 and D3. Okay. And now I'll move this one a little bit to the right because I need some room here. And this one row down because I need room here. So now the constraints say shipping from source S1 must be equal to 30, at least not greater than 30. So I have to add this plus this plus this. These are the shipments. So I'm using, and let me write it so that you can remember, it's sum. That's what I'm entering now here. Sum, open parentheses, and highlight the first row. This means that I added x11 plus x12 plus x13. So instead of putting it here, I just put it here as an Excel function and copy it down here because now I have to add the other 2 for source number 2. Then I'll create a constraint with these. Then I want to see the shipment into each demand point. So I'll write sum for you to remember. It's a sum of the column. Okay, and 1, 2. I added the two cells that belong to x11 and x21. And copy the other two for the other columns. I'm almost there. The only thing missing, and this is the objective you told me that you saw, but now I'm placing it in this cell instead of one of the cells that used to be here. So it's the total cost. It's equal to. Now pay attention. What do I calculate? 14 times, oh, sorry. What do I have to do? 14 times this variable plus 16 times this variable. It's the objective function. Well, I'm using sum product. You open parentheses. Highlight the first matrix. You don't have to press F4 here because I'm not going to copy this function anywhere. It's the only place in the model I'm calculating it. So comma, and then select the variables. Solver knows what to do. It doesn't have to work with a vector against another vector. It can work with a matrix against another matrix, but the two matrices must have the same dimensions. Exactly. And that's what I did. Exactly the same dimensions. Now you see why. And this will be calculating the cost. Once I have solution here, solver will place a solution here. I'll get the result here. Okay, I'm going now to solver to enter this model. So I'll have to delete the model that I have because it's no good anymore. Everything is different. Now, first of all, the objective function. The objective function is in cell, in this case, O14. This is where I placed it. Minimized. Variables. Now what I select 1, 2, 3, 4, 5, 6. 6 variables. So variables do not have to have one line. It can be a range of a matrix. Now I'm adding constraints. Add. I'll do it twice. First of all, I'll have exactly the signs that I have here. So supply, the two supplies together must be less than or equal to, which is already less than or equal to here, the two available supplies, capacities. And then I add the demand constraints. The demand constraint have the actual shipments into the demand points has to be at least as large. So I change it to greater than or equal to the demand. So you see, now I added this. And now I'm ready to solve. This is checked. This is simplex. I'm solving the problem. Look at the solution here compared to the solution here. Same solution. See? Well, what you see here is very easy to read, even if you have a large table, because if you put real names of cities here, to start with, the output will include your names. And then it will be very, very, very easy to read and see how much is shipped from each city to each city. So if you have 5 by 12, it's nothing. It goes in one screen. It's small. Now I want you to see something else. What would have happened if I insisted on equal, 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 equal? It should be the same solution. Should make no difference, but I want you to see something. So I'm changing the constraint, change it to equal to. And the second one also to equal to. Okay. Now I'm send, it should give me exactly the same solution. Well, I'm minimizing the cost. Oh, the good news, I got exactly the same for 550 on the minimum total cost. But the shipping plan has changed. If you compare the 20 here, it used to be 5. So what happened here? There is more than one optimal shipping plan. It has multiple optimal solutions. All of them will end up having $540 total shipping costs, but the structure of the shipping is not necessarily the same. Very important thing for management to know, because what if they realize that here they call for shipping of 15 units from source 1 to destination 2, 15 units. This is a route that goes from source 1 to destination 2. Only that this route is going to be closed tomorrow because of some construction on the road. Then they have another option to not use this route from 1 to 2 and still have exactly the same cost. Give them another option. Multiple optimal solutions is very good for management. Give them flexibility. So how do we know to obtain such a, how do we even know that there are other options? This is something I want to show to you next time. There is a way of telling that there is more than one optimal solution. Solver does not give you alternative solutions. It gives you one. But in the sensitivity report, you see some things that typically occur when there are multiple optimal solutions. The book is talking about this briefly. I'll also show to you something that makes it very easy to obtain alternative solutions. I just need time for that. If I don't have time for that, we will not do it, because it's more important for me to do the sensitivity report, which I'm going to do. Yeah, I have 10 minutes. That's for the basic sensitivity on transportation, and the rest of it will be next time. If I finish that, I'll do the multiple solutions also. Okay, so I'm going back to the, oh, somebody was chatting with me. How do you know if you select max or min? Oh, who asked? I think I answered this. Alex. Alex.
Yeah, you already answered. Thank you.
Oh, okay, I did. Thank you. Okay. So you can ask me by talking to me, Alex. Then I will answer right away, like Mahmoud did. And you see, you are not too many guys. 1, 2, 3, 4, 5, 6, 7, 8, 9. You can talk to me. It's fine. It's not a problem. And so now I am going to share with you again the PowerPoint and do some sensitivity. Okay. So you see problem 16. Sensitivity analysis, and I want to raise your attention to the word I used here, single objective coefficient. So I'm going to do sensitivity analysis for objective function coefficients, but I say a single objective coefficient. Why would I even say it? Remember, sensitivity analysis is done for a single coefficient at a time. That's because the next slide, I'm going to develop the last topic in sensitivity, which will allow for more than one coefficient change. And it will be true for the objective, more than one coefficient is changing, and then for the constraints, more than one right-hand side. And they both use the same rule, so that's for next time. This is why I wrote single here. Let us, for convenience, denote S for sources and D for destinations. First question. The unit transportation cost from S1 to D3, source number 1, demand point number 3, is increasing by $3 per unit. It's the unit transportation cost, so it's a coefficient in the objective function. Each time when you see such a change, realize where is the change in the model, objective coefficient or a constraint. So I am locating it as the objective coefficient. I mentioned to you, this is the one. What happens to it? Increasing by $3. Intuition say, hey, then don't ship 10 units anymore on this route. It becoming $10. It's almost 50% more expensive. Find other solution, other transportation plan. Answer, wrong. Do not find another one. Why? $3 increase falls inside the allowable increase. 3 is less than 4. So therefore, the optimal shipping plan is not changing. It remains optimal as is. As is. So, so that's why it's important to know that, because sometimes intuition does not give you the correct decision. And then besides, you can estimate the total cost after the change, and you don't need to rerun the model in order to know, because you know that if you do, you'll get exactly the same solution. The only difference would be that this is 10 instead of 7. Okay, so why not take the old total cost equal to 540 and add to it the additional cost on the route X13. How much is it? $3 per unit more, and $10 remain unchanged. So $30 more, and you have the total cost. And this is one thing I want you to see on the basic, I call it basic, what is a single change. Now I say, here's a different change. The transportation cost from S1 to D2, from S1 to D2, which is now 16, is dropping to 15, dropping to 15. So now you are looking at the allowable decrease, and you see that 1 is well within the range. So therefore, because 1 is less than 16, the allowable decrease is much larger than 1. And you can recalculate the total cost because the optimal solution also doesn't change. So now it will be the 540 here, but now you have a change of -1. You pay $1 less on each unit shipped, and you have 15 units like this, so you get the total cost. This is the basic analysis on range of optimality. This is what is called, for the objective function coefficient, single change. I'm leaving the constraints for later discussion because first you will see me talking about simultaneous changes of both the 7 and the 16 at the same time. Now we have a problem. Sensitivity analysis is not covering this. So that's what I need to do next time. After we are done with that, I'll go to the constraints and do single change and multiple changes. That's the plan, I guess, for next time. Okay. So that's what I wanted to do today. And as you see, I'm going simultaneous changes, not for today. And this is all what I wanted to talk to you today. Any questions? Okay, so it was clear, I hope. I'll have to end because I have to finish the recording, and I can only do it if I end the meeting. So if there is no question, I'll end the meeting. So see you in 2 days, guys.
Bye.
Bye-bye.